In our last video, we talked about measures of center. So you know the mean of a set of data, which we represented if we had x bar as the sum of all of the data divided by the number of data points that you had, or sometimes we would just write that with a sigma over n. And the median is the middle of a set of data after you put all of the data points in numerical order, either ascending or descending, doesn't really matter. Now we're going to look at trying to find measures of spread in addition to measures of the center. So how do you compute that? Well, it really is going to completely depend on which measure of center that you're using. Whenever you're using a median, we're going to use something called the interquartile range. I'll explain that in a moment. And when you're using the mean, instead for the measure of spread, you're going to use either standard deviation or variance. Standard deviation tends to be the favored one. And again, all three of those are new terms for you, so let's start computing them. By far the easiest to use are with medians. And so if we've got a median, I ran a rand int from 1 to 10, 15 numbers, and I went on ahead and put them into numerical order. So we know about the median. The median for a set of 15 is the 8th data point, so 3, 6, 7, 8. That particular 3 is my median. And obviously this one down here is my low value. This 10 up here is my high value. And if I look at basically what the median does, because I have an odd number of data points, I've got 7 below and 7 above, I can compute a median on the upper half and the lower half. So looking here on the lower half, that is sort of the lower median, and that 9 is something like the upper median. So I'm going to call this, bringing up a new word for you, quartiles. This is going to be quartile 1, and this will be quartile 3. All right? But what's a quartile? Go back to the prefix on the word quart, like quarter, 1/4. Quartiles basically divide the data into fourths. And what we're really looking at is the subscript tells us how many fourths of the data we've already gone by. Now, the low value here is clearly that bottom one. Technically, I could call that Q0. Nobody really does that, but it's subscript 0 because that lower one is higher than 0/4 of the data. Then it ought to make sense why quartile 1 is called Q1. It is higher than 1/4 of the data. The median would be quartile 2. It's higher than 2/4 of the data. Quartile 3 should now be obvious, and the high is quartile 4. Nobody really uses Q0, Q2, Q4 because we just call them low, high, and medians. But Q1 and Q3, hopefully now you get an idea why those subscripts are what they are. So, interquartile range is really just looking back at the measures that you had before. An interquartile range is going to be defined as Q3 minus Q1. And just a straight up definition, so in this case it would be 9 minus 2. My interquartile range is 7, and that gives us some sort of measure of spread. I'm looking from like the bottom quartile, the quartile of the bottom half and the quartile of the top half, and the difference between those gives me some sort of measure. And because of that gap, it's sort of like the width of the middle 50% of the data. And so that tells me I may have some values that are a lot higher or a lot lower. Don't really know about outliers yet. But if I know what my interquartile range is, I know where the middle 50% is, then everything else is, it's sort of like describing the center, the heart of the data. So I know the median in this case was at 3, and the interquartile range went from 2 to 9 for a width of 7. And from this, I'm actually going to finally be able to define what an outlier is. And so far, we've sort of had this qualitative, does it look really extreme? How extreme is extreme? The flat definition of an outlier is you are an outlier if you are more than 1.5 IQRs beyond either Q1 or Q3. All right, so in this case, our IQR was 7, and 1.5 IQRs in this case is at 1.5, so 10.5. I would need to be 10.5 units below 2 or above 9. 2, remember, was my Q1, 9 was my Q3, and if I am anything more than that, then that's going to be considered an outlier, and that's actually how we're going to define them from now on. You need to be more than 1.5 IQRs from your box, from those two, the lower quartile and the upper quartile. An extreme outlier is defined, this is more a little bit of trivia. I don't know that this is really going to be that much on the test, but extreme outliers are defined as more than 3 IQRs beyond the edges of Q1 and Q3. So there are some implications in how we'll graph these in a moment, but that's your basic definition for now. All right, a graphical representation of this is I could try to find a box-whisker plot. Now, what I remember from up above here is there were sort of 5 summary points. That's what we're going to call these guys. Those 5 quartile points, Q0 through Q4, are called summary points. And those numbers for us are 1, 2, 3, 9, and 10. So let's come back down here. I'm going to put a dot at 1, at 2, at 3, at 9, and at 10 for this data that I have. And what I do first is I'm going to draw vertical lines at Q1. I'm going to draw a long one for the median and draw another one at Q3. So this is where my Q1 was located, this was my median, and this was Q3. And from Q1 to Q3, draw in a box. And then from the edges of the box, draw lines out to your high and your low point. And those are our whiskers. So this is sort of a box holding the middle 50% of the data. And the whiskers sort of show the extreme 25, the low 25% and the high 25% of the data. All right. We will talk a little bit more about, what do you do when you've got outliers in the data and how far, like some variations on the whiskers. But for now, this is basically a really quick representation of the data. The box is showing you the middle 50% and the whiskers extend to the remainder of the data points. So when you're dealing with a median, the basic way to measure spread is to compute an IQR, which also gives us a way to talk about outliers. But what happens when you have a mean? Before, we had actually already encountered one measure of spread, and that was a residual. So in a much smaller data set, let's say 3, 6, 7, 8, and you can quickly verify that the mean of this data set is 6. If you remember, residuals are really just the signed difference of each data point from the mean. So 3 happens to be 3 units below, 6 is 0 units off, 7 is 1 unit off, and 8 is 2 units off. And there are my 4 residuals for those 4 data points. Now, we're going to start making a small difference for a short time here between a sample mean. If I had a data set that I had gathered through some sampling procedure, we said X bar was the mean of that small sample, of that data sample. If I actually, for whatever reason, knew the entire population, I had every single data point there ever was from an entire population, I would call that mu. That's a Greek letter for M, mu. And this is always for a population. Greek letters we use for populations, and then Latin letters we use for samples. Both of these symbols, X bar and mu, represent a mean. But we use the X bar when it was a sample and the mu for a population, and that's going to become important in just a moment here. All right. Another thing that we had in mind, this was a curious property about all means. So if I had every single X value within a data set, and I know the mean of the data set, whether it's the population, and I'm using the population symbol for right now, or it was a sample, all the X values either for the population and the population mean, or the sample and the sample mean, all those residuals will always add up to 0. So I had a lovely measure of spread, some measure of spread, residuals, but the problem is residuals always add up to 0. The signs of them keep canceling out. That's causing a bit of a problem because I'm going to get the exact same sum of residuals no matter what kind of data set I get. It's the signs that are causing an issue, so we need to eliminate them. The really obvious way to do that is to just say, well, some of them are positive, some of them are negative, so let's just eliminate all the negative signs. And that's an entirely reasonable assumption. But here's a problem. If you were to look at an absolute value, think about absolute value graphs from algebra, from your previous algebra classes, you know that those graphs look like V's. They have corners. And for reasons that deal with calculus, if you've done any exploration of a derivative, you know that calculus does not like corners. They become non-differentiable. It's beyond the scope of this course, but taking the absolute values of all of our residuals is going to cause us problems. So the next best thing that we can possibly do is take the square of them. Squaring certainly eliminates all of our negatives. And then, the squared residuals will actually add up to something. But the problem here is we actually get a couple twists, implications into our data set that we didn't have before. And one is when you square things, you distort their values and you do so unevenly. If a value is 1 and you square, nothing really changes. But if the residual was bigger than 1, it gets much bigger. And in fact, the farther you are from 1 above, the greater the implication of squaring. So squaring residuals is an uneven effect. And in particular, that will have a huge effect on outliers. An outlier is already a data point that is far away from the mean, which means its square is going to become extremely far away from the mean. This procedure of squaring residuals is extremely sensitive to outliers, so you're going to need to be aware of that for your data. All right, but this actually isn't that difficult. If we wanted to, I could very easily compute the square of all my residuals, and then in some ways, a measure of spread is nothing more than sort of like a mean of all those squared residuals. And that introduces us to two different ways of measuring spread. One is I could compute what's called a population variance, and all that is say, take each data point, subtract the population mean, assuming you knew that, square them, so there's our squared residuals, and I want to add all those up and divide by the number of data points. That's all I'm doing. It's like a mean squared residual, and that is something called population variance. Population because I'm dealing with the population mean, and our symbol for that is another Greek letter, sigma, and I'm going to square it, and the square is just representing that I'm dealing with these squared residuals. Now, this is, as we said, a distorted view because I've squared all those distances. One way to try to bring that back is to take the square root of all of those squares. Now, this doesn't eliminate the squaring factor because remember, you're square rooting a sum, and the square root doesn't distribute over all of that, but it does something to try to eliminate some of the effect of the squaring. That creates something called a standard deviation, and its symbol is just going to be sigma to try to indicate that the squaring effect is somewhat mitigated. So variance is nothing more than a mean squared residual. Variance is just this mean squared residual, and standard deviation is just the square root of that. But again, it's really important to note that if you had any outliers, if you had any extreme data values, both of these measures are going to be extremely sensitive to them. So what would happen if you didn't know the population mean? Well, that's not bad. We could always just approximate that. Whenever we don't know the population mean, we just took a sample and we found the arithmetic mean of that. We had a sample mean. So those two things are really, really close to each other, but they're not exactly the same measure. Here's a subtle implication that's going to come out for us as we adjust for samples instead of populations. Remember back when we were talking about means, we realized that if I already knew the mean of a data set, and the data set had however many elements in it, we had an example in the last video of, imagine there were 5 test scores that were going to be, and you wanted your final test score average to be, let's say, a 90, and you had 4 test scores. We figured out what your 5th test score had to be in order to get the sample mean that you would wanted. The reality of this is, if I know the mean and there are n elements in the overall data set, if I know all but one of those data points and the mean, I can actually compute that last point. So in a way, sort of talking about the amount of information that I have available, if I have n data points and a sample mean, I'm in some ways redundant. If I know the n data points, I can always compute the mean, or if I know all but one of the data points in the mean, I can compute the last data point. So in some ways, if you have to compute a sample mean, you're going to lose a touch of information. And we're going to talk about this a lot more in the second half of the year. But we're going to talk about here degrees of freedom. Whenever you are dealing with a sample mean, instead of n measures on the data set, you actually have n minus 1, and here's where this is going to come into play. All right, for variance, remember variance was the sum of all of these squared residuals. But in order to compute the mean, because I've sort of lost a degree of freedom, I've lost a little bit of information in computing the sample mean because I didn't know the population, I'm now going to divide by n minus 1. And that's going to give me, using the Latin letter for variance, s squared. And the sample standard deviation is, again, the same thing without the square, and it is just the square root of variance. So the big difference in this case is, notice whenever I'm using a sample, computing a sample variance, I'm going to divide by n minus 1 instead of n. And it's what happens every single time when you have to estimate the population mean. It's very rare that you would actually know the mean of an entire population. So this sample variance is actually the far more common usage. Very rarely will we use sigma squared. We'll almost always use s squared for variance and s for standard deviation, and these are just for samples. Okay, so a quick way to compute, lots of theory. Let's actually do this. We figured out before there's a data set. We knew the mean was 6, and therefore my residuals are -3, 0, 1, and 2. And remember, ultimately what we're getting here is some sense of the mean squared residual. So all of my residuals are right there. I now need to square them all. So -3 squared, 0 squared, 1 squared, 2 squared. And so their sum is going to be 14. So the sample mean of squared residuals, that's really just sample variance, which we had called S squared, and that is just the sum divided by n minus 1. Remember, the n minus 1 is reflecting that I actually had to approximate the mean, so I sort of burned up a data point in doing that. So now my sample variance is going to be 14/3, which is something really close to like 14.7. And the sample standard deviation is just the square root of that. So S is going to be the square root of 14/3, which is going to be about 2.16. And I will now sort of move on. This is kind of a pain. The good news is you're not going to have to do this very often, but technically you ought to know what they come from. Remember, variance is nothing more than sort of a mean squared residual. The denominator you'll have to adjust. All right, so probably not going to need to compute these by hand, but there are several Inspire calculator commands that you could use to compute this. And I will do a brief video just sort of confirming all of these as a follow-up. Thanks.